In this video, we're going to talk about some relationships. We're going to talk about the Ka. We're going to remind ourselves about something we quickly identified earlier, the pKa, and how we can use those along with a couple of other pieces of information to determine the concentration of the basic form of our pair and the acidic form, right? So we're going to do that all together, setting up some other things, right? So let's consider, right, our typical weak acid dissociation, the way we've written it, right? Right? So we tend to, in this class, think about our acids, at least in these problems, in the Arrhenius sense, just because it saves us some writing, right? But we could just as easily consider those acids in the Bronsted-Lowry sense. That is, that our acid reacts with water to make hydronium ion plus our conjugate base anion, right? And I'm using the language already, right? When we do that, right, we've got an acid and its conjugate base. Right? And so we say those two are a conjugate acid-base pair, right? And so, there's a language there that we can use, and it bleeds over. And so even if we write it in an Arrhenius sense, we tend to talk about these two species as a conjugate acid-base pair. Now, if we write out our equilibrium, right, if we write our Ka expression, and I'm going to write it from the Arrhenius equation, right, you get concentration of hydrogen ions times the concentration of the conjugate base anion divided by the concentration of undissociated acid. If you've watched the other videos, you've heard me say that, right? But we can rearrange this to look like this. All we have to do is pull that hydrogen ion out front, and then we've got the ratio of our basic form to our acidic form off by itself. And I will admit, this is my preferred way to look at this, right? There is another way, and that is to do a log-log transformation of this expression, right? So if you take the log of the left, you get the log of the Ka, and if you take the log of the right, you get the log of the concentration of hydrogen ions, plus, right, remember when you multiply it's plus, the log of the concentration of the basic form over the concentration of the acidic form, right? Now, if we rearrange this by moving, right, by subtracting this from both sides and by subtracting this from both sides, then what we get is an expression that looks like this. And I'm going to write it over here so we have room. The negative log of the concentration of hydrogen ions ends up on the left. The negative of the log of the Ka ends up on the right. And then you've got that log of that ratio of your basic form to your acidic form. Right? Now we're out of room, so we'll have to move to another sheet. Right? Clearing some space here, right? That rearrangement gives us a different equation, right? We might recognize, right, that this is our definition of pH, right? And this is our definition of pKa. And so we get a new equation relating the pH and the pKa and the concentration of the basic form and the concentration of the acidic form. And this equation is called the Henderson-Hasselbalch equation. Right? And these are useful in situations, right, where we're dealing with, since I have space in the middle, right? These are useful in situations where we're dealing with weak acids, right? And their conjugate bases. In situations when, if we worked it out with an ice table, we can ignore the x that we're adding or subtracting, right? This gives us another way to sort of quickly organize our problems when we suspect that we can ignore our x in the ice table, okay? Now, I will admit that my preference is to use this form of the equation because it comes from our definition of the Ka. And if we know our definition of the Ka, we really can't forget that equation, right? Where the Henderson-Hasselbalch equation is a derived equation, we have to remember a little more, and I always like to remember as little as possible. And we can work any problem from the Ka expression. I'll show you a couple using both, but by and large, I'm going to use the Ka expression to solve the majority of these problems. Okay, so let's consider a solution of butyric acid, HC4H7O2. It has a nice Ka of 1.5 times 10 to the minus 5, right? And so let's say we know that the concentration of hydrogen ions, right? We measure with a pH meter and we find it's 3.0 times 10 to the minus 5, right? The concentration of hydrogen ions is 3.0 times 10 to the minus 5, right? Well, if we use our Ka expression, we know that the 1.5 times 10 to the minus 5 is going to be equal to the concentration of hydrogen ions times the concentration of butyrate ions divided by the concentration of undissociated butyric acid, right? But we know the concentration of hydrogen ions, right? So we can substitute that in there. So we get our 1.5 times 10 to the minus 5 is equal to 3.0 times 10 to the minus 5 times the concentration of the butyrate ion divided by the concentration of undissociated butyric acid, right? And if we divide both sides by this 3.0 times 10 to the minus 5, then we're going to end up with 1.5 times 10 to the minus 5 divided by 3.0 times 10 to the minus 5 equals 0.5, which is going to be equal to our concentration of our butyrate ion divided by the concentration of our butyric acid. Which means, right, anytime this is true with this acid, we have essentially, right, the concentration of butyric acid is equal to twice the concentration of butyrate ion, right? We know that ratio. Then all we have to do is find one or the other, and we can find the other one, right? And so this gives us a quick way of determining this important ratio, okay? So there it is, worked using the Ka expression. Then now I'll show you one, the same problem using the Henderson-Hasselbalch equation. So if we start the problem in the same place, right, the hydrogen ion concentration is 3.0 times 10 to the minus 5. That is a pH of 4.523, right? Just for fun, right? And then if we remember our Henderson-Hasselbalch equation, right, the pH is equal to the pKa plus the log of our concentration of our basic form, which is our butyrate ion, divided by our concentration of undissociated butyric acid, right? And I say it that way. Oh, that's H7. Let's see here. Let's make that a little smaller. Right, erase that. So I can get the right thing in there. Right? Oh, looks like I need to erase it here too. Right there. No, I had the 4 right. C4H7O2, right? Writing faster than I can talk. Okay, right? So we've got that, so we can substitute in what we know, right? Our pH is 4.523. Our pKa is 4.82. And then we've got the log of our ratio of C4H7O2 minus, right, our butyrate ion divided by our undissociated acid. Oh, and I was going to say, I say it that way to remind us it's not the initial concentration of acid, it is the undissociated acid after the system has reached equilibrium, right? So, right, we take 4.523 minus 4.82, that's going to equal negative 0.297, right? Close to that. And that then is going to be equal to the log of that butyrate ion divided by the concentration of undissociated butyric acid, right? And so that means 10 to the negative 0.297 should equal that ratio. I don't know why I keep writing a 4 there. Probably because I do too many problems with acetic acid. And we get 0.50, which is exactly what we got before, right? So we have two ways to get there. We can use the Henderson-Hasselbalch equation, or we can just use the Ka expression. I will admit I prefer to use the Ka expression, but every problem I'm going to do could be done using either one. So here we can summarize what we just found, right? We started with our butyric acid. Here's our Ka, here's our pKa, right? If this was our pH or if this was our hydrogen ion concentration, we found that the ratio of base to acid was 0.5, right? That is, there's twice as much of the acidic form as there is the basic form, right, under those conditions. So let's look at a different condition, right? Let's look at a pH of 5.42 or a concentration of hydrogen ions of 3.802 times 10 to the minus 6, right? Now, I said I would do this using the Ka expression, so we get, right, 1.5 times 10 to the minus 5 is going to be equal to our 3.802 times 10 to the minus 6, that's our hydrogen ion concentration, times our concentration of our butyrate, divided by our concentration of butyric acid. Right? So we get 1.5 times 10 to the minus 5 divided by 3.802 times 10 to the minus 6, and we get 3.95. And, we'll make that approximately 4, right? As being equal to the concentration of butyrate ion divided by the concentration of undissociated butyric acid. I apologize for my friend texting me in the middle. You don't have to grab your phone. Okay, now a couple of things to notice here, right? We've worked this out, but if we go back and look, right, note here, our pH here is lower than our pKa, right? Which means there's more hydrogen ions than at the Ka, right? The concentration of hydrogen ions is greater than the Ka. And there's more base than acid, right? Or, I'm sorry, more acid than base under those conditions, right? If the pH is lower than the pKa, or the concentration of hydrogen ions is greater than the Ka, there's more acid than base form in the solution, right? Down here, our pH is higher than our pKa, right? We're more basic. The concentration of hydrogen ions, right? Note this number is lower, right? Our concentration of hydrogen ions is lower than the Ka, and we have more of the basic form, right? The amount of basic form is greater than the amount of acidic form. So that is a qualitative comparison you should be able to make. You should be able to just look at the value of the pH and compare it to the pKa and know whether this ratio is going to be less than 1 or whether this ratio is going to be greater than 1. Okay? That's something you should be able to do.